Now, at this point in the course, we're going to start our section on thermodynamics or thermal energy. We'll discuss various properties of related to the heating or cooling of different systems, whether we talk about air masses or ocean water masses or a pot of boiling water or whatever consideration we have. We are going to be talking about their thermal properties. And the way we're going to start this discussion is to talk about what we mean by temperature, what we mean by heat, what we mean by heat capacity, and finally the property of thermal expansion exhibited when objects or matter is heated up. So we'll go through these one at a time and begin our discussion now. Okay, the discussion is going to begin with the concept of temperature, something that we are all familiar with. We are all familiar with measuring the temperature of the outside air with a thermometer or the inside air with the thermometer, and it is a number that corresponds to the warmth or coldness of the object, as we're all familiar with. It is also a property that is based on the molecular speed or vibration of molecules. And as such, we will see that it has a microscopic interpretation. The other two features of temperature is that there is no upper limit on how hot an object can be. We can go to millions of degrees, such as in the core of the sun or in other stellar objects. But there is a limit on how low the physical temperature of an object can be. And because of the fact that it is a measure of the kinetic energy of a molecule, that there is a absolute zero temperature or a temperature below which we can no longer go below. And at that point, when that temperature is reached, in this case, universally, in fact, it is about approximately minus 460 degrees Fahrenheit. We've never experienced that. Probably the coldest we've ever been is minus 20 in a deep winter freeze, but one could go substantially lower than that. However, when we reach a limit where the temperature is reached approximately negative 460 degrees, all thermal motion of the molecules has been frozen out. That is to say that they would be stationary. There would be no movement of the molecules when that temperature is reached. Therefore, it does not make sense to go below that temperature because, or nor is it physically even possible, because once all of the kinetic energy of the molecules has gone to zero, we cannot go lower than that. So there is a lower limit, and that is called, which we've said here, is approximately minus 460 degrees Fahrenheit. Now, one way to interpret temperature on a microscopic scale is to state and let you know up front that the temperature is proportional to the average translational kinetic energy 1/2 mv squared of the molecule in a substance. And regardless of whether this is a gas or a liquid or a solid, there is motion of the molecules. Now, for tightly bound solids, they don't move great distances, so they is really a measure of how fast they are vibrating or rotating or jiggling in place. That is another form of kinetic energy. It's not the 1/2 mv squared, but it is the fact that they are vibrating. Like, for example, if I had a molecule like salt, which is sodium and chloride, the sodium is attached to the chloride, but they are oscillating towards and away from each other at a given frequency. And then the higher the temperature, the more more amplitude or more energy goes into that vibration of the molecule. The way that a thermometer works is by the expansion or contraction of a column of liquid mercury in a narrow glass tube. So, for example, if the thermometer is taken outside on a very hot day, for example, where the temperature outside is much higher than the temperature inside, then the temperature of the um, of, of the thermometer, or the mercury inside the thermometer in the tube, will begin to expand. And a general property is that objects that are heated up will expand in their volume, and objects that are cooled down will contract in their volume. So, in the case of liquid mercury moving in a narrow glass tube, if it's when it's cooled down, or we take it outside on a very cold day, then the heat from the mercury is lost. That is to say, it gets colder, and as it gets colder, the mercury shrinks. And because it's confined to the volume of a narrow glass tube, then the level of the mercury begins to drop, and the gauge besides that column of glass indicates what the temperature is, which has been calibrated by the vendor who has made the thermometer for us. Um, now, the object that we are measuring could be a pot of liquid water or soup. We could have a thermometer that is stuck in the pot of liquid on the stove, and as we turn on the burner and add heat, uh, the the molecules of the water or soup will become more energetic. They will have more kinetic energy, 1/2 mv squared, and that will be transferred to the um, uh, to the kinetic energy of the molecules inside the liquid, mercury. So the mercury, which in this case, the glass tube of mercury, which has been stuck into the pot of water, will eventually equilibrate with achieve the same temperature as the pot of liquid. And when that happens, the mercury will stop rising, um, as long as the temperature of the water or the soup has not changed. So there will be a change in or a transfer of heat from the liquid pot from the water to the mercury if it's at a higher temperature than the mercury, and when it equilibrates, that is to say that the temperature of the liquid mercury is the same as the temperature of the pot of liquid water, then the mercury no longer rises in the glass tube. So we then have what's called thermal equilibrium, and when that occurs, there is no net flow of heat um, from the object, or in this case the pot of water, to the thermometer, or there is no transfer of heat from the thermometer back into the pot of water. So that is what we mean by thermal equilibrium. Um, and when this occurs, we have an accurate measure of the static temperature of the water. Now, the temperature scale for the glass thermometer, the glass liquid, the liquid mercury in a glass tube, can be measured or given in terms of units that are degraded or indicated on the side of the thermometer. And some thermometers come with two scales of temperature. One of them is Celsius, and the other one is Fahrenheit. In the United States, in the weather reports, we are most familiar with the temperature scale of Fahrenheit. It's the one that we use quite frequently the most. And on that scale, we can think of a couple limits or values that mark that scale fairly accurately. One of them is the freezing point of water. How low does the temperature have to go before water begins to freeze? And as most of us are familiar with, that temperature is about 32 degrees Fahrenheit. On the other end of the liquid scale of liquid water only remains a liquid at atmospheric pressure until the water reaches a temperature of 212 degrees. We call that the boiling point of water. So that is how we gauge it in our ordinary way of thinking. And the other gauges that we have for our familiarity is that room temperature is about 70 degrees Fahrenheit, and um, a very hot day in the summer will be about 100 degrees. A very cold day will be anywhere from 0 to minus 20 degrees Fahrenheit. So um, that gives us an indication or a range of how we can become familiar with those scales. Now, in science and in physics, we typically use the Celsius scale more frequently than we do the Fahrenheit scale. And the reason being that the scale of the temperatures is more easy to interpret based on the freezing point of water and the boiling point of water. So the way in which this system is defined or derived is to when we measure when we reach a temperature where water begins to freeze, we call that 0 degrees Celsius. And as we heat up the water, when it reaches a temperature of plus one, when the water begins to boil, we call that temperature 100 degrees centigrade. So the Celsius measurement varies from 0 to 100 for the normal conditions of liquid water on Earth, and that's how it is basically defined. Also, worth bearing in mind that that the Europeans, if you ever see the BBC news or European news, you will see their weather reports are given in the Celsius in the Celsius range. In case that last part was cut off, I apologize for the disruption. The Europeans use the Celsius scale for their reporting their atmospheric temperature daily weather reports. So on a very hot day, which we call 100 degrees, the temperature in Celsius will be about plus 38 degrees, and the freezing point of water is 0 instead of 32. We can draw or write a simple formula that shows how to convert from to the Fahrenheit temperature scale or from the Celsius temperature scale to the Fahrenheit or the other way around. So I've written that for you. If I know the temperature in Celsius, for example, given to us from a European weather report, I can multiply that by 1.8, add 32, and that gives me the temperature in Fahrenheit. Or conversely, if I want to solve for the temperature in Celsius, I can solve this equation for Tc, and in that case, I first of all subtract 32 degrees from the Fahrenheit scale and divide by 1.8. So this is the way in which we can do conversions fairly simple. Now, the other scale that is used defines the 0 degree point as the lowest temperature that one can achieve. It is the absolute, the 0 degree Kelvin is the lowest temperature that that can be achieved. And at this point, 0 degrees Kelvin, there will be no thermal energy left in the system. That means that all atoms have been frozen out to lose all of their kinetic energy. And since kinetic energy cannot be negative, it's 1/2 mv squared, temperature cannot be negative on the Kelvin scale. 0 is the absolute, that's why it's defined that way. It is the lowest temperature for which objects can have any, for which they, in which all of the thermal energy has been frozen out. Now, for the way we calculate it in terms of the Celsius temperature is simply to add 273 degrees. So in the Kelvin scale, if we want the temperature in Kelvin, we add 273 to the temperature in Celsius, and that gives us the result that we need. Now, in this slide, you're asked to consider uh, two pots of boiling water, one which has 1 liter of boiling water and the other has 2 liters of boiling water. And we are given also that there is twice as much molecular kinetic energy in the 2 liter of boiling water as the 1 liter of boiling water. And that is simply because there are twice as many molecules. So if the energy per molecule is the same, then we will obviously get twice as much molecular energy in the 2 liter pot as the 1 liter pot. And since that molecular kinetic energy is a measure of its thermal energy, we would say that the thermal energy of the larger pot is larger, or actually the internal energy would be a better word, is larger than the energy of the 1 liter pot. But based on this consideration, the temperature is related to the molecular kinetic energy per molecule. And as we stated earlier, the temperature is proportional to the molecular kinetic energy per molecule. So, therefore, if the temperature is the same in the two pots of water, then the kinetic energy per molecule will be the same. The difference is there are twice as many molecules in the 2 liter pot. So therefore, there will be twice the total molecular kinetic energy in the 2 liter pot as the one. But then the temperature must be the same because the temperature is related to the kinetic energy per molecule.